All right. This is the lecture 1 out of 3 on milliequivalents, millimoles, and milliosmoles. And we'll do milliosmoles at the end. We're only focused today on milliequivalents, really, for the main part. And this is probably a review for most of you. So that's what I'm saying. You feel free to study away in your biochemistry. But I'm a little worried because this was kind of what was on the midterm where a lot of you kind of struggled on that calcium chloride equivalent question there. And so that kind of skill is definitely what we're covering in this section. So some of you may still benefit from a little bit of a review and definitely going through some of these practice problems. So these aren't difficult, and it is a kind of a review for hopefully many of you, but I'll hopefully make sure you can do these type of questions. And I also say this is an important section because while you may not be making a lot of ophthalmic solutions, and therefore, you know, the whole isotonicity thing may or may not be something you do all the time, but I guarantee you next year in your P2 year in your lab, you do a lot of IV admixture stuff. And doing milliequivalents and doing electrolyte calculations for sodium and calcium and phosphate and chloride and all these things are an important part of institutional hospital practice. And so these basic calculations and these types of examples are important. So it definitely is a skill you need to get down. It won't take you long, I don't think, but make sure you have it, all right? So with that, let's get started with the idea of what is an electrolyte, because all these examples you're going to see through here, it seems like I'm always talking about sodium or potassium or calcium or chloride or magnesium or sulfate or something like that. Because there's not that many products we use in biology, and certainly in clinical practice, that are electrolytes. Electrolytes are chemical compounds then. When you put them in water, they dissociate, usually completely. Not always, and we talked about that a little bit earlier, but generally your electrolytes are things that are going to dissociate. So the classic example here is sodium chloride. So here is our solid sodium chloride, right? When we put it into water, though, what happens is it dissociates into the chloride coming apart from the sodium. They come apart, all right? They get surrounded by water. When they come apart, when they dissociate, they expose an electrical charge. Drug molecules, which are not electrolytes, they may be soluble, but they don't fall apart. They don't expose an electrical charge. So we're leading to this idea of a milliequivalent is essentially counting the amount of electricity. And the reason you only count electricity for electrolytes is because they separate and expose their charge. Drug molecules do not, okay? So you don't measure drug molecules by counting electrolytes, but counting charges, or milliequivalents, I should say. But your sodiums and magnesiums and chlorides and calciums, things that you use to treat all sorts of acid-base disorders, any sort of conduction problems, there are lots of times where, again, you do need to give an electrolyte, and therefore you're going to measure it using milliequivalents, okay? So getting back in here is, again, that when we take these compounds that are electrolytes that separate, you get cations. Those are the positive charged ones, okay? The main ones to know are sodium and potassium and calcium and magnesium. Those are the ones we most often deal with in medicine and biology. They're usually salted together with their cations, the anions, which are the negative ones, are going to be your chloride, bicarbonate, phosphate, and sulfate. Okay, so those are the combinations of things together. Right? So, would you agree with this? We've been counting molecules. Now, hopefully you can do this. Can you take the weight? I'm going to talk about here. We can take the weight of something and convert it to the number of molecules, the moles or the millimoles. All right? So you could have one sodium molecule and one calcium molecule. Are there the same number of molecules? Yes. Would they produce the same amount of chemical activity? And what I mean by chemical activity for electrolytes is that what is an electrolyte? Why is it special? It dissociates and it exposes a charge, right? So from one sodium, would you get the same number of charges as you would get from one calcium? No, and because you're going to use the valence, you look at the charge on the molecule. So when you count electricity, the amount of chemical energy or the chemical activity, once these things are in solution and break apart, then you end up wanting to count the electricity generated by those molecules, or those ions, if you will. And that's why even though you might have one molecule of sodium and one molecule of calcium, the same number of molecules, that doesn't mean you get the same amount of chemical activity. So we're going to count that chemical activity in the units of milliequivalents. All right? So let's just make sure you can do this. This is key. You need to be able to go from the weight of a product to its number of molecules. What do you need to use from this table that helps you do that? You convert from weight to molecules using the what? The molecular weight. Okay, are you okay with doing that? So if you take the weight in milligrams and divide it by some products or chemicals molecular weight, you can convert it to the number of molecules. Easy breezy. This is where there's kind of a trick here. How do you go then from millimoles, let's see if I can do my color thing here. How do you go from millimoles to milliequivalents? This is what's important and a little bit new for this. What did we say? We said electricity. You're going to use the valence. Make sure you understand what that term means, because that's how you're going to convert from the number of molecules to the number of milliequivalents, or the amount of the chemical energy from that product, by using its valence. So make sure you know what I mean by valence. You look at the molecule and you look to see whether it's positive or negative, how many charges are exposed when that product is separate. So look at aluminum. Its valence is 3 because it has plus, plus, plus. There are 3 charges exposed when that separates. It can either be positive or negative, but in the end we're talking about the total number of charges exposed by that, okay? So again, the key ones to make sure, you know, calcium is a +2. Okay, we've talked about sodium and potassium. We do a lot of magnesium. Okay, and I won't keep harping on that, but if you look at the charges there, that's where you get the valence from, and the valence number gets associated with the milliequivalents. The milliequivalents just says, okay, if I have this many molecules, milliequivalence says this is how many charges I get from those molecules. And why is that important? Because you're counting the amount of energy, the chemical activity of a product, just not the number of molecules. And that's why it can be important. Okay? So this is just a simplistic example of how we're going to do all of these calculations here. And you're either going to go from the weight of something and tell me how many milliequivalents that is equivalent to, or you're going to go from how many milliequivalents you have back to the weight of something. And so you always go through this process. So let me just emphasize this. What you do is, if we start on top and go by weight, in this example I say 160 milligrams of calcium, the cation. Okay, so we have just a cation, we have 160 milligrams of just calcium. How would we convert that from the weight of that calcium to the number of calcium molecules? We would divide it by the molecular weight. Since the molecular weight of calcium is 40, we would divide by 40 milligrams, and therefore milligrams cancel, and that would give me the number of molecules of calcium. And lastly, that number of molecules produces how much electricity, how many charges, how much chemical activity from that number of molecules. Well, this is what's important. You have to go to the valence on the molecule, and that number is what you're going to put as the milliequivalent. So the valence value is then the number of milliequivalents per 1 millimole of that product. In this case, calcium, so again, millimoles cancel, and when I multiply that across by 2, then I have the number of milliequivalents. So 160 divided by 40 is 4. 4 times 2 is 8. So again, the 160 milligrams of calcium produces 8 milliequivalents of calcium. Easy breezy, I hope. Okay. This is just going to backwards, so I don't want to belabor that point. If you go, though, from milliequivalents, then you have to multiply it by the 1 millimole over the valence number. So again, if the valence number is 2, that goes down below here. So does it make sense that in this case, if I'm starting with milliequivalents, I multiply it by 1 millimole over the number, the valence in milliequivalents, so that this cancels. Now I'm back in molecules, and remember to convert from molecules to milligrams. In this case, I would need to multiply by the formula weight so that millimoles cancel, and I'd end up with milligrams in the end. Okay? Any questions on that? All right? All right, so let's do some questions. I know these seems easy. Well, I'll show you the answers. I'll read you the question first here, just for fun. A normal potassium level in the blood, this question says, is 17 milligram percent. 17 milligram percent. Express this concentration in terms of milliequivalents per liter. Okay? I'll give you the molecular weight for potassium, and the valence of potassium is 1. All right? It's easy breezy, except for the hardest part to that is re-express. And are you okay with your units and concentration? Milligram percent is a concentration. And all the question is asking for is expressing that amount in a different units. Instead of milligram percent, convert it to milliequivalents per liter. So let's start with milligram percent, okay? That's a weight per volume, because we want the potassium in the blood. So the weight units in this case are milligrams per what? What does a percent mean? Percent is 100, right? And since it's weight per volume, it would be what? 100 milliliters. So could you convert 17 milligram percent as being the same thing as 17 milligram per 100 milliliters? That's one trick to this question. If you can understand that and just rewrite it that way, that's half the battle. Because then, starting with that, all you have to do is convert your units. And you can do either milliliters to liters or milligrams to milliequivalents, but let's start with doing the weight. So let's start by converting our units of milligrams to milliequivalents. So you don't go straight there. You have to convert milligrams first to millimoles. You go from the weight of something to the number of molecules. And to do that, you divide by the formula weight. So since the formula weight is 39, then I multiply by 1 millimole over 39 milligrams of potassium. Now I'm in millimoles. All right? So to go from the number of molecules to the amount of electrical energy, what do you look at? The valence. What is the valence on potassium? 1, right? So that's why you get 1 milliequivalent of potassium for every 1 millimole. By doing that, millimoles cancel, and I'm now in milliequivalents. Okay? So I'm good in the numerator. The only last trick on this question is I'm still in milliliters, if you remember down here. So how are we going to get rid of the milliliters? So let's multiply by 1,000 milliliters per 1 liter, and then my final units, therefore, will be milliequivalents per liter. And if you do that math from left to right all the way over, you'd get 4.36 milliequivalents per liter. And all this question is doing is practicing your unit conversion to be able to convert from one concentration, milligrams per milliliter, to a different concentration of milliequivalents per liter. Okay? All right, let's do a more interesting one here. Let's start with a commercial product. We have potassium bicarbonate, and we're going to start with a tablet that has 2.5 grams a weight, 2.5 grams of potassium bicarbonate with the formula there. And this is where the chemistry, you got to know your chemistry, you got to be able to deal with chemical formulas, because in this case, potassium bicarbonate is KHCO3. That's important, okay? So we know the formula and we know its molecular weight is 100. So how many milliequivalents of potassium are supplied by that one tablet? All right? So where do we start? Well, let's start with the tablet. We have one tablet that weighs how much? 2.5 grams, all right? So first step was, what I did was convert grams to milligrams because I want to be in millimoles. So I'm going to convert grams to milligrams by multiplying by 1,000. So I just take 2.5 grams times 1,000 so that my units cancel. I'm now in milligrams. How do I convert my weight to molecules? By essentially dividing by the formula weight. So I have 1 millimole of potassium bicarbonate per 100 milligrams, okay? And the 100 milligrams comes from where? That's the molecular weight, so that's why I'm dividing by the molecular weight. I'm now in the number of molecules. Is everyone okay so far? I've converted my weight from grams to milligrams, and now from milligrams to the number of molecules, which is millimoles. Now, this is a new step we didn't practice before, so this is an important step here. Not a hard one, but this is an important step. I want to know the milliequivalents of potassium, right? But I'm in the millimoles of potassium bicarbonate. I have to go from potassium bicarbonate to just potassium. And you do that by looking at the formula. So I guess I ask you, if you look at this formula, would you agree when it dissociates, how many potassiums do you get? 1. How many bicarbonate molecules do you get? 1. Okay? For 1 molecule of the parent compound. So that's all I'm doing here is I'm converting from the number of molecules of potassium bicarbonate to the number of molecules of just potassium. I would argue there is 1 potassium molecule for every 1 molecule of potassium bicarbonate. How did I know that? What did I look at? The formula. I looked at the chemical formula of the parent compound. It's KHCO3, 1 potassium, 1 K for every 1 KHCO3. So it's 1 to 1. Now my millimoles of potassium carbonate cancel, and I am in just the number of molecules of just the potassium. So last, to calculate how much electricity comes from that amount of potassium, I multiply by its valence, which again is 1, so I just multiply by 1 milliequivalent. So my millimoles of potassium cancel, and my final answer will have units of milliequivalents of potassium. You do the math all the way across, and you get 25. Any questions on that part? This is, okay, there's 2 things, just as we keep going through. This step, let me do blue here, and this step. This one and the red one. You have to, now once you get into the number of molecules of the parent compound, you have to first convert to whatever electrolyte part you want, whether it's the anion or the cation. You have to count the number of the anions or cations in the parent molecule first. Then you have to use the valence of that anion or cation to convert to the amount of electricity. So those 2 steps are going to be important, and we'll keep practicing those, all right? So next question, how many milliequivalents of lithium are provided by the daily dose of 300 milligrams of lithium carbonate? And again, I'll reemphasize, the formula here is very important. It's Li2CO3 with a molecular weight of 74, all right? Okay, these are not hard. What do we start with? Well, let's start with our total number of tablets. How many tablets are we doing? 4 times 300 milligrams per tablet will let me cancel my tablets. I'm now in my weight of lithium carbonate. Let's convert from the weight of lithium carbonate to the according number of molecules by multiplying by 1 millimole of lithium carbonate has 74 milligrams. Ooh, I'm still in blue, but that's fine. I'll remind you that's where that comes from. So now my milligrams cancel, and I'm in number of molecules. Okay? Now this is what I meant by this is an important step. How many of you, and this is where some of you missed this on the midterm with the calcium chloride that was CaCl2. This is the step you missed, because to convert from lithium carbonate to just lithium, you have to look at the chemical formula. How many lithiums are in one lithium carbonate molecule? 2. It's Li2CO3, right? There are 2 lithiums that come apart when this thing dissolves in water. You get 2 lithiums for every 1 parent compound of lithium carbonate. Where does that come from? That 2 comes from here. Make sure you understand. That value 2 is from the Li2. And that's why we're multiplying the fact that you get 2 lithium molecules every time you have just 1 lithium carbonate. Is that clear? That's really, I think, what messed a lot of people up. So make sure that part of it is clear. All right? Now, don't forget, we're now in just the molecules of the lithium. We still want to measure the amount of chemical energy from that, the amount of electricity from that. So let's look again at the valence. And for lithium, it's still just 1. But make sure that's why I'm multiplying it by 1 milliequivalent over 1 millimole. I only get 1 electrical charge for every 1 molecule. So now that cancels millimoles, and I end up in milliequivalents of lithium. You do that math all the way across, and you get 32.4. Are these getting a little repetitive? I hope. It's unit canceling and making sure, though, the trick about counting molecules and then counting valence is extremely important. It's the only thing that can mess you up, but a lot of you get messed up. All right, so here is a bonus question. I've got 2 of these. If any of you downloaded the slides before yesterday, you may not have noticed this in there, or certainly even my recorded lecture. I added 2 bonus ones because I thought this lecture was kind of short. So I thought, well, let's do a couple of other interesting examples. So if you have this one, great. If not, there you go. We'll do it together. It's not Percocet. Don't get all excited. What is the name of this drug? Percogesic. It is actually over the counter. It's not that exciting. So Percogesic backache relief capsules contain 580 milligrams of magnesium salicylate tetrahydrate. Okay? So there's the big fancy formula there. And again, this is where some of you get scared when you see these large chemical formulas. Stay calm. Are you with me on that? It's okay. There's lots of letters and numbers there, but it's all right. Stay calm on this. There's got this big long formula and a molecular weight. So first of all, you're going to see a lot of hydrates. I just want to make sure I understand this, because I'm not a chemist, I'm a pharmacist, but I need to know a little bit of chemistry. A hydrate is a what? It's a water molecule, right? If you hydrate water, it's okay, stay hydrated, right? A lot of you have your water bottles, that's good. What is a tetrahydrate? 4 waters. What is a dihydrate? 2 waters. A hydrate, a water. Okay, so the dot, whatever with the water on it, that's okay. A lot of the chemicals we use come in that form. And I can't even tell you why sometimes, but a lot of times the actual active ingredient you use comes in a hydrated form. It's probably from a stability standpoint. Anyways, we can deal with it. It's also got this big old molecular weight. That's fine. Question asks, how many milliequivalents of magnesium will the patient receive each day if they take the normal analgesic dose of 2 tablets 3 times a day? Okay? Well, to fit my equation here on the end, I kind of cheated a step. How many tablets per day then? If they're taking 2 at a time and they do that 3 times a day, how many is that? 6, hopefully. Okay, so I start with 6. They're taking 6 tablets per day. And we said there are 580 milligrams of magnesium salicylate tetrahydrate in each one. So if I take 6 times 580, that would give me the total weight of the compound that I'm getting per day. Let's convert that to the total number of molecules per day by multiplying by 1 millimole over its, again, molecular weight. So the molecular weight is where that number comes from. And I do that so milligrams cancel, and now in the molecules of this big old parent compound. Do I really care? What's the only thing I care about in terms of that big molecule? It's an electrolyte. It will separate, and you'll get magnesiums to separate from the hydrates, which will separate from the salicylate. All right? So in the end, I guess, this is this idea of let's separate what I'm interested in. What I want to know is the milliequivalents of the magnesium. So how many magnesiums are in this formula? When it dissociates, I get 1 of these, 1. I get how many of these? 1. And how many of these? 4. Do you agree with that? I mean, if you think about it breaking apart as an electrolyte, then that's what it would split into. And since I'm only interested in the magnesium, I can see that I get one magnesium molecule out of every one magnesium salicylate tetrahydrate. So I can convert now and go from moles of my parent compound to just moles of magnesium. All right, be careful. This is our first little change here. That's simple, but now let's go to the amount of chemical energy. What is the valence on magnesium? It's 2, it's not 1. So do you see why I'm going to multiply that times 2 milliequivalents from magnesium for every 1 millimole? This is an example where it's not 1 to 1. Since the valence is 2, I get 2 electrical charges for every 1 molecule. So that's why in the end I multiply this value by 2. And then if you multiply all the way across, you get 18.78. And again, the final units when everything cancels, because again that cancels with that, we get 18.78 milliequivalents of magnesium. Okay? You don't seem overly challenged. This is good. All right, so we'll go one more in this kind of vein. But let's make this a little bit more difficult because this is now, instead of just coming from a tablet, let's do it from a solution. We have an ophthalmic solution of EDTA, which is edetate disodium. And it's a chelating agent. It binds things. And so sometimes they're using this more now is they put it in an eye drop. And it binds some of the things. So if you've got some things that can form plaques, actually, with certain conditions, it'll bind those. Or if you get eye exposure to chemicals and so forth, they'll put these drops in there to help bind up that chemical to keep it from interacting with your eye. So regardless, it does come as a concentration of 3%. And since it's EDTA 3% ophthalmic solution, it would be 3% weight per volume. All right? So from that concentration of solution, it wants to know how many milliequivalents of sodium are contained in this 10 milliliter bottle. And again, I will still remind you, this is the important information you have to have is the chemical formula. So if, as an electrolyte, when it dissociates, what will it dissociate into? Let's go ahead and answer that. How many of the edetate molecules, and this is the edetate, how many of those do I get from every 1 molecule? 1. How many waters do I get? 2. How many sodiums do I get? 2. You see where you can kind of look that even ahead of time to kind of count those number of molecules, all right? So let's go ahead and answer this question. Well, it wants to know how much total sodium milliequivalents is in from the whole bottle. So the bottle's 10 milliliters. So can you still set up your concentration? So let's take 10 milliliters times the 3% weight per volume. Since it's weight per volume, it's grams per milliliter. And since it's a percent, it's 100 milliliters. So we have 3 grams per 100 milliliters. Multiply that by 10, and I cancel my volume, and I'm now in grams. Let's get to milligrams by multiplying by 1,000. So that will cancel out my grams, and now I'm in milligrams. I'm in the weight of my sodium edetate, or my disodium edetate, EDTA. All right? I want to go to molecules. So let's go ahead and divide that weight by its molecular weight. So again, times 1 millimole over the molecular weight. That converts it from weight to molecules. Okay? And since we've already counted the number of there, would you agree that we've established there are 2 sodium molecules from every 1 molecule of the disodium edetate? Okay, that's why I chose that. It's disodium. That should be kind of obvious, I hope. You get 2 sodiums. So now my millimoles of the parent molecule cancel, and by multiplying by 2, I know the number of molecules of just the sodium. I'm in molecules. Last step to go from molecules to electrical energy is to convert it by multiplying by the valence. And since the valence on sodium is 1, there's 1 milliequivalent for every 1 millimole. Millimoles cancel, and I'm in milliequivalents. And my final answer then numerically would be 1.78 milliequivalents of sodium. All right? Let's keep it going. All right, so here's another question. It says, how many milliequivalents of potassium are represented in a solution that contains, and you can see there's 0.5 grams of 3 different variations of potassium. Potassium acetate, potassium bicarbonate, and potassium citrate. What do all 3 of those ingredients have together? Potassium, right? So they're all various forms of potassium. And what we want to know in the end is the total amount of potassium from that amount of all 3 of those ingredients. And that happens a lot. When we do our calculations for TPNs here in a little bit, we don't always want to give all of our sodium in sodium chloride. Even though we need a lot of sodium, what we may not want is a bunch of what? chloride. So instead of sodium chloride as our only source of sodium, we might also include sodium acetate. So we can still get sodium, but not so much chloride. So there are often times where we mix salts so we can get the total amount of one of the electrolytes, but without having that amount of total of the other anion or cation, whichever it is we don't want. So in this case, we want a lot of potassium, but we don't want a lot of any either acetate, bicarbonate, or citrate, so we're going to split it up between them all. And so here's the idea. I think a big part of this question is we're all starting with the same amount of weight. Do you think we're going to get the same amount of milliequivalents from those weights? Because they're different chemicals. What are things that will influence the amount of milliequivalents? I would argue it's twofold. It has to do with the molecular weight. Would you agree these two molecular weights are pretty similar? But look at the big difference here. Would you agree those molecular, that's like 3 times the molecular weight of the other two. So even just trying to predict the amount of milliequivalents we'll get. So I don't know, will that 3 times the molecular weight give us 3 times more or 3 times less? We'll see here in a minute. The other thing to factor, what haven't I factored into it? So our starting weight, our molecular weight, but what is the other thing that factors into the amount of milliequivalents we'll get? Is the chemical formulas. So we'll have to take into account the chemical formulas when we do this, all right? Regardless, it's all solved the same way, and yes, you probably all know how to do this. So I'll try to go through this a little more quickly. If I just start first with the potassium acetate, remember we've got 0.5 grams, we're in weight. So if I start with that weight, then I'm going to convert grams to milligrams, so I'll multiply by 1,000. Then I'm going to divide by the formula weight, so that's where the formula weight comes in. That cancels my weight and gives me millimoles, so I'm in the number of molecules. And let's look at the formula here. I get 1 potassium here, so that's why I have 1 there for every 1 parent molecule. So that converts from the parent molecule to just potassium. And then lastly, the valence there is 1, so that's why I'm going to multiply by 1, and that'll convert from my millimoles of potassium to my actual milliequivalents. And I get 5.1. Okay? So there are 2 things that I would say that play a role here. Clearly, the larger the molecular weight, the smaller the number of millimoles that you will get since you're dividing by it. Okay? But if you look at the chemical formula, the larger the number of molecules of that electrolyte within the molecule, the greater the number of milliequivalents. Okay? And then lastly, the valence will play a role. Okay? So let's compare what we get. So let's start with our potassium bicarbonate. It's got the same 0.5 grams to begin with, convert it to milligrams, convert milligrams to millimoles by dividing by its molecular weight, which is 100, which is very close to the 98. Would you agree? And since it also still has 1 molecule for every 1 potassium for every 1 potassium bicarbonate, it's 1 to 1, and it's still got the same valence. You'll see we almost get the same number. So what is the only difference between those 2 numbers? Is the difference between 98 and 100. Okay? So even though they're a completely different chemical, so potassium bicarbonate versus potassium acetate, since the molecular weight of both of those are about the same, converting from a weight to the number of milliequivalents gives you about the same number of milliequivalents. So let's use our last example, which is the potassium citrate, convert its weight and go through that same process. Now, though, the weight's divided by 324 versus 100. Would you agree you're dividing it by 1/3 more than you did before? But how come our answer isn't 3 times less than our previous answer? Because how many potassiums are in 1 molecule of potassium citrate? What's the formula? 3. There is K3. So we have to multiply it by a 3. So that 3 on top by the number of potassiums in the parent molecule offset the difference in the greater molecular weight. And that's why when you do the math, it's a little bit lower, but not much. It's 4.6. Okay? So I think that, anyway, so the same process. Hopefully then the final answer would be simply to add all those up. Your 5.1 from the potassium acetate plus the 5 from the potassium bicarbonate plus the 4.6 from the potassium citrate gives you a total of 14.7. So the overall answer to this question would be 14.7 milliequivalents of potassium, because it doesn't matter where the potassium comes from, which of those compounds, we just added it all up together. But again, I think this question was mainly designed for you to kind of look at some of the differences between formula weight and the actual formula itself to be able to determine what the final milliequivalents end up being. Okay, you don't seem too excited. Let's do calcium, and calcium is a little more exciting because it doesn't have just a valence of 1, and you use it quite a bit. And I like this question because it's the first time we're going to go backwards. So bear with me on this. If you've turned me out, this is a little different of a variation of a question. So let's read it. It says, you need to prepare an electrolyte solution that contains 4.6 milliequivalents of calcium per liter. How many grams of calcium chloride dihydrate should be used to prepare 20 liters of this solution? There's a lot of numbers here, and it's going backwards from what we've done before. So can you handle this? Where would we start? Well, we're trying to know how much to prepare. How much? What volume? 20 liters. Let's start with the volume we're trying to prepare. So I would start with the 20 liters, and that's where that comes from, 20 liters down here, times its concentration. And we were told that we want 4.6 milliequivalents per liter. So that's where that comes from. So let's take 20 liters times 4.6 milliequivalents per liter. My liters cancel, and now I'm in milliequivalents of calcium. Okay? But I want to get to weight. You don't go from milliequivalents to milligrams until you can convert it into what first? Millimoles. It goes milligrams to millimoles to milliequivalents, or milliequivalents to millimoles to milligrams, all right? So we've got to go to millimoles. So our first step is to convert the milliequivalents of calcium to the number of molecules of calcium. And to do that, in equivalents, we've got to use the valence. So since the valence on calcium is 2, there would be 2 milliequivalents of calcium for every 1 millimole. That's why you end up dividing by 2. I just know this is where a lot of you will struggle, is making sure you know whether to multiply or divide by certain things. In this case, we're dividing by it because we want to multiply by the fact that we want 1 millimole on top over 2 milliequivalents. That's what cancels milliequivalents and now gives me just millimoles of calcium. But I don't want the weight of calcium. This is important. I want the weight of what? Calcium chloride dihydrate, essentially. So I've got to go from this number of molecules to this number of molecules. And it's not rocket science, but again, this is an important step. Depending on the compound I give you, it's not always 1-to-1. But in calcium chloride, since the formula is what? CaCl2, the amounts of calcium is just 1. There's 1 calcium molecule for 1 molecule of calcium chloride. So that's why it's 1-to-1. But setting it up like this allows me to cancel my millimoles of calcium, and now I really am in millimoles of calcium chloride dihydrate. And I left out the dihydrates here just because they were getting in the way, making it too long. But here I included it for the weight. Because now to convert to the weight, let's take the molecular weight of the dihydrate, set it in there, and let's multiply. That way my units of millimoles of the calcium chloride cancel, and I'm now in the weight of the calcium chloride. So now I'm in milligrams of the calcium chloride dihydrate I would need. The last step is simply to convert that to grams from milligrams by multiplying by 1 gram over 1,000 milligrams, so milligrams cancel. My final units would be grams, and now going left to right, your number would be 6.76, doing the math, and that units are grams of calcium chloride dihydrate, all right? So we went some milliequivalents of just one of the ions, in this case the cation, calcium. From the milliequivalents of that, we converted it to the number of moles of calcium, to the number of moles of calcium chloride, and then to the weight of that calcium chloride. So hopefully you're seeing those steps. Going one way or the other way doesn't matter, but it's step by step by step. Okay? Let's do this question, and I'm going to do it the Larry way to begin with, which means it's the hard way. You really wouldn't have to do it. There's a cheaty way. Let's see if I do it my way, and at the end, let's see if you could have found a cheating way to do it a little bit faster. So it says, a patient is receiving an intravenous infusion of 5% dextrose with 0.45% sodium chloride with 3.1 grams per liter of potassium chloride at a rate of 100 milliliters per hour for 24 hours. So how many potassium chloride or Cater tablets would be equivalent to that? Okay, so if each one of those tablets contain 1,490 milligrams of potassium chloride. Okay, so we're trying to find the equivalent amount. Am I missing something? You guys just hanging out? Did it? So, can you guys hear me in Wichita at all? Okay, well, hopefully this mic will pick that up, and I'm turning it off and back on again. It does look like it's dead. All right, well, I'll leave it on in case it comes back on, but there we have it. Can you guys hear me okay in Lawrence? All right, I'll try to speak up a little bit more, and again, Wichita, yell at me if I cut out. I'll try to make sure I'm staying by this mic, though. All right, so to summarize this, we've got an IV bag that's giving us both dextrose and sodium chloride and potassium. Do we care about the dextrose or the sodium chloride in this question? We do not, so ignore that information. That's what makes some of these questions a little more difficult than maybe they need to be. Let's focus on the potassium. So if I'm getting that amount of potassium in IV, I want to convert from IV to oral. So let's first calculate how much potassium I'm getting from my IV infusion. And I know there's a lot of numbers there, but in the end, this infusion, the amount of potassium is the amount they need over what time period? 24 hours. So let's start with 24 hours. And let's just look at the IV and have the IV infusion tell us how much potassium they're getting. So if I start with 24 hours times 100 milliliters per hour, hours cancel, and I'm in milliliters. Then let's multiply it by the concentration. Now, I cheated here a little bit. The concentration they gave us in the question was 3.1 grams per liter. Would you agree that's 3,100 milligrams per 1,000 milliliters? So I kind of just re-expressed that and kept a step, but that really is the same units as that. I did it so that my milliliters will cancel, and I'm now in milligrams, the weight of the potassium chloride this person is getting every 24 hours in their IV. Well, let's convert that first to molecules, so we'll divide the weight by the formula weight, and remember the formula weight comes from the addition of the potassium and the chloride. So you add those together, and the total weight is 74.5, so now I'm in millimoles of potassium chloride. Again, there is one potassium in every one potassium chloride, so now I can cancel those, and I'm now in the molecules of just potassium, and since the valence is 1, I just multiply by 1 milliequivalent over 1 millimole, and I get the number of milliequivalents. So would you agree that IV in a 24-hour period is providing the person 100 milliequivalents of potassium? So all I have to do now is start with that and convert it back to the amount of weight I would need for these tablets. So to go backwards, I then take milliequivalents times its valence on the bottom to convert to millimoles, so that cancels that, so it's 1 millimole per 1 milliequivalent. I go to the parent molecule, since it's 1 to 1, then I can go from potassium to potassium chloride, and I can go from the molecules of potassium chloride to the weight of the potassium chloride by multiplying by its formula weight, and now I'm in milligrams. And then to convert from this, well, all I need to do is that there's 1,490 milligrams of potassium chloride in every one tablet. So if I divide that value by 1,490, milligrams of potassium chloride cancel, and I get 5 tablets, doing the math from left to right. Okay? So that was supposed to be an example of how you went from time and basically calculated volume and volume to milligrams and milligrams to milliequivalents, and then took that target and worked backwards to be able to get the number of tablets. Does anyone know how you could kind of cheat and get a lot easier? Would you agree, let me turn this to blue, that if you did all of this, what are your final units at this point? Milligrams of potassium chloride, right? You could have just taken this answer at this point and gone right to this step right here and not even had gone to milliequivalents, because you already have the weight of potassium chloride. Before you converted it to molecules and milliequivalents, you could have just divided it by the fact that there was 1,490 milligrams of potassium chloride, a weight per tablet, and gone straight there as well. So you didn't have to do it the long way, but if you did, then you got to enjoy the fantastic learning experience of converting from weight to milliequivalents and milliequivalents back to weight. Okay, so either way would have worked. All right, let's get to my banana question, man. I love this question. It says, a person taking a diuretic is advised to eat a banana daily. A banana contains, and this is not always consistent, but this banana contains approximately 140 milligrams of potassium per ounce. How many milliequivalents of potassium would be consumed in a banana weighing 120 grams? So let me ask you this. What's a common drug? Are patients, you guys fill potassium supplements for patients? Absolutely. A lot of potassium supplements, because a lot of patients are on diuretics like furosemide and things that cause potassium loss, so we have to replace that. Do you have to be on a pill form of potassium? Can't you get potassium from a dietary source? And this is a good example. You can get potassium from a banana. How much potassium are we going to get from this 120-gram banana? All right. I like this question only in the sense that it still makes you do your unit conversions. You have to be careful with the way you set up your formulas and cancel things out to get the right answer. So let's start with our banana. It was 120 grams. Well, our potassium was expressed as 140 milligrams per what? Per ounce. So we have to convert from grams to ounce. So let's start off by multiplying 120 grams by 1 ounce is 30 grams. Okay, so if we divide by 30, then we convert from grams to ounces. Then we can multiply and actually determine the weight of potassium in our banana. So again, if I multiply 1 ounce times 140 milligrams per ounce, then ounces cancel, and I'm in milligrams of potassium. The nice thing is I'm already in the amount of my electrolyte, so all I have to do is convert the electrolyte from its weight to its number of molecules by dividing by its formula weight. So that's where that comes from, and that cancels out the weight of potassium, and I'm now in the number of molecules of potassium. So lastly, to convert to the electrical energy, just convert the valence over. So let's multiply by 1 milliequivalent for every 1 millimole. A number of molecules cancel, and I get 14.4 milliequivalents of potassium. Okay, so that's how much you get from a banana. What is most of your strengths of your tablets that you guys dispense? 8 milliequivalents, 10 milliequivalents, 20 milliequivalents. So a banana is maybe a better way than taking a tablet. It's probably a lot cheaper too. So anyways, this patient though is getting tired of eating bananas. I don't know why. I love bananas. But anyways, this patient in the next question says, okay, no more bananas. They want to do is how many milliliters of a 10% implied weight per volume solution of potassium chloride elixir would be needed to provide the same amount of potassium. So whatever amount we're getting from our banana, let's also now get it from this 10% solution instead. So obviously, let's take our target that we had. This is how much they're needing to get. We'll bring it back down to here. And now we need to convert it to the volume of this elixir. And since the volume of that elixir is given in a weight per volume, we're going to have to go from milliequivalents back to weight to calculate the volume. So let's just do it. Milliequivalents, remember the valence is 1. So if I multiply by 1 millimole over 1 milliequivalent, I get millimoles. To go from potassium now to potassium chloride. This is kind of a new step here, be careful. But it's a 1-to-1, since there's 1 potassium in a potassium chloride. I can convert from molecules of potassium to molecules of potassium chloride. I can then convert that number of molecules to its weight by taking its formula weight and multiplying so that millimoles cancel. And now I have the weight of potassium chloride. But I'm in milligrams. And my percent concentration isn't milligrams, it's what? Grams. So let's convert milligrams to grams by dividing by 1,000. So that cancels milligrams, and I'm now in grams. Finally, I can use my 10% because 10% is 10 grams per 100 mils. So let's set it up and multiply it by 100 mils over 10 grams so that my grams cancel. And my final answer multiplying across would have the units of milliliter, and it would be 10.7 milliliters. Okay? This is a good example of the kind of questions you've got to be pretty good at doing. I'm not saying they're hard here, but it's kind of the idea of going back and forth from either weight to milliequivalents or from milliequivalents to weight or volume depending on what we're doing. So those are good example questions. Last idea, and it's not even a calculation, but I love this idea. You noticed, I went through a bunch of examples, but didn't we talk about potassium a lot? Some sodium, some calcium. There's not that many things we do these calculations on. Because in medicine, there's not that many drugs that are electrolytes. And why do we worry about this? Because electrolytes, are they even that important? Why do you guys stay hydrated? Is staying hydrated important? You get dehydrated, then it throws off your concentration in your blood of what? Your electrolytes, a lot of it. And that could be the potassium and the chloride. Think about all of the sports drinks and everything else. Maintaining electrolytes are important for your cardiac conduction, your nervous system, all sorts of stuff. So carefully regulating and replacing this relatively small number of things is still important. All right? But in the scope of things, there are lots of other drugs out there that are not electrolytes. So let's the ones shown here on the bottom, clobetasol and ciprofloxacin. I give you this big fancy chemical structure. Are you guys looking forward to MedChem? There it is right there. In one slide summary, that's your MedChem coming at you, just so you know. Isn't that made out of the same stuff? Isn't it carbons and oxygens and chlorides and fluorines? Isn't it the same thing as a lot of the electrolytes we've been talking about? Yes. So I guess it's getting down there. Do we measure drugs by counting electrolytes? Why wouldn't we, for the clobetasol and the ciprofloxacin, for the example it talks about for chloride or fluorine, calculate the number of milliequivalents of chloride that come from clobetasol? We just did that for potassium chloride, right? We just did that for sodium chloride. Why don't we measure the amount of chloride or fluorine or anything from these other normal drug molecules that aren't electrolytes? Because those molecules are what? Covalently bonded. They don't dissociate. What we've been doing is talking about measuring these things in milliequivalents for products that are electrolytes. And what do electrolytes do in water? They dissociate. They expose that electrical charge in that valence, and therefore you can count those chemical energies. You stick a ciprofloxacin in, and you might get one ciprofloxacin molecule. What charge do you get? Nothing. It's not an ionic charge. It doesn't dissociate. It doesn't expose any of that. So the answer to this is, can there be milliequivalents from those parent molecules? And the answer is no. All right, why? Because it doesn't dissociate. It doesn't separate. It's covalently bonded. It's part of that molecule. So we don't measure milliequivalents for the majority of drugs out there. This is well, I kind of skipped this thing in the middle. This is kind of important, but it can be kind of confusing. We've talked a little bit about this. However, a drug like penicillin, again, is just like the ciprofloxacin. It doesn't come apart. But it is formulated in a tablet as a salt. You know what I mean by a salt? It is when it does have maybe a negative, the drug has a negative charge, so it does need to be salted or combined with either a sodium or a potassium in the case of the penicillin V potassium. They are sometimes salted with different things. Or you've heard a lot of your drugs are hydrochloride, right? Memorizing for the top drug exam. Do some drugs have salts along with it as the drug name? Okay, so yes, you could actually measure, in this case, the amount of potassium in a penicillin V potassium tablet, and that's interesting, but is that how you dose it? Do we give a penicillin V potassium for the amount of potassium in there? No, we do it for the amount of penicillin. We can account for the amount of potassium that has to be there so it can be formulated in a way, but we don't really care about that amount of electrolyte in those dosage forms. Those dosage forms are there to provide the active